All right, folks, the key for LQ5, it's posted at Blackboard, but I thought I would run through some stuff real quick. Still got some issues that we need to take care of. 1A, you do need to recognize that is a geometric series. R is 1.002, which is greater than 1, therefore it diverges. In B, 3 over 5 to the n, well, that can be rewritten as 3 times 1/5 to the n. It is not 3/5 to the n. In any event, it's a geometric series. R equals 1/5, which is less than 1, so it converges. C, the series inverse tangent of n. Quite simply, the limit as n goes to infinity of inverse tangent n is pi over 2. That tells us it diverges, thanks to the nth term test. One more time, making a note. The nth term test does not ever tell anything about convergence. It never has, it never will. It's only divergence. For D, the key is n to the e over n to the pi. That can eventually be rewritten as 1 over n to the pi minus e. Pi minus e, that number, pi minus e, is definitely less than 1. So it's a p series where p is pi minus e, which is less than 1. Therefore, it diverges. Some of you tried to use the nth term test for divergence here, but you know, you didn't convince me. You had an indeterminate form that you tried to then make a claim. So be careful. Part E, I looked at that series and I said, well, I'm going to compare it to the series n squared over n to the 4th, which simplifies down to 1 over n squared, which we know is a p series. P is 2, which is greater than 1. We know that p series converges. So then I'm cranking the problem through the limit comparison test. Yes, I have to show this work so that when I have my conclusion, the series converges via the limit comparison test with the series 1 over n squared. I have shown enough work here to convince a Michigander. Part F, the series 1 over n squared natural log n. Well, I compared that to the series 1 over n squared. Again, p series that we know converges. And then here I wrote down the preamble of the direct comparison test because I know 1 over n squared natural log n is less than or equal to 1 over n squared. I know that inequality is true thanks to our denominator argument. Remember, the denominator argument is only a valid thing to say when the numerators of the fractions are the same. So I now know the series 1 over n squared natural log n. It does converge thanks to the direct comparison test with the series 1 over n squared. Number 2, do the following series converge absolutely, conditionally, or diverge? Again, state a reason why and show enough work to convince a Michigander. First off, the alternating series test does not tell you anything about absolute convergence. I started this problem by saying, all right, if I take the absolute value of each term of the given series, the absolute value of each term gives me the series 1 over n squared plus 10, which I thought, why don't I compare that to the p series 1 over n squared, which I know converges. So I think I can do a direct comparison test. So I wrote down the preamble to the direct comparison test. A sub n less than or equal to b sub n. A sub n is 1 over n squared plus 10. B sub n is 1 over n squared. That inequality is true thanks to our denominator argument. The numerators are the same. So that tells me the series 1 over n squared plus 10 converges via the direct comparison test with the series 1 over n squared. And if I know the series 1 over n squared plus 10 converges, which was the absolute value of each term of my original given series, then I know the original given series converges absolutely. Part B, again, I started off by saying, well, if I look at the absolute value of each term of the given series, I get the series n squared plus 1 over 3n to the fourth plus 3. I'm going to compare that to 1 over n squared. Again, P series, I know it converges. Here, I can't do a direct comparison test, but I can crank it through the limit comparison test. When I crank it through the limit comparison test, I get the limit to be 1/3, which tells me the series n squared plus 1 over 3n to the fourth plus 3 converges thanks to the limit comparison test with the series 1 over n squared. And since the series n squared plus 1 over 3n to the fourth plus 3 was the absolute value of each term of the given series, I now know my given series converges absolutely. 3. Use the integral test to determine the convergence or divergence of that series. Well, I look at the function of the reals, inverse tangent x over x squared plus 1. Integral test, so I have to evaluate that improper integral, rewrite it, a basic u sub, and I end up getting the limit to be 3 pi squared over 32, which tells me the improper integral converges, which tells me the given series converges thanks to the integral test. All right, number 4, I'm telling you that that series converges. So find an upper bound for the remainder in terms of n. Well, r sub n, the remainder, is bounded by the improper integral from uppercase n to infinity, x e to the negative x squared dx. So I went off to the side and I evaluate that improper integral, and I get the improper integral to have the value of 1/2 e to the negative n squared. So that tells me r sub n is bounded by 1/2 e to the negative n squared. Lower bounds and upper bounds, L sub n and U sub n respectively, on the exact value of this series. Well, the lower bound is equal to S sub n plus the integral, the improper integral, n plus 1 to infinity x to the negative x e to the negative x squared dx. Well, that improper integral is pretty easy for me to evaluate because I did a lot of the hard work in part A. The upper bound is S sub n plus the integral from n to infinity x e to the negative x squared dx. And I know the value of that improper integral thanks to part A. So those are the lower bounds and upper bounds respectively, what L sub n and U sub n is. So we're going to find in part C an interval in which the exact value of the series must lie if you approximate its sum using the first 5 terms. Well, the first thing I do is I add up the first 5 terms, and I get the sum of the first 5 terms, that's S sub 5, to be 0.4048813986. So the lower bound, L sub 5, is S sub 5 plus 1/2 e to the negative 36. And the upper bound, U sub 5, is S sub 5, the sum of the first 5 terms, plus 1/2 e to the negative 25th. And so I know the lower bound is 0.4048813986. The upper bound is 0.4048813986. So I know the sum of the series from n equals 1 to infinity, n e to the negative n squared. I know that sum is somewhere between the lower bound and the upper bound. Well, since the lower bound and upper bound are the exact same number to as many places as my calculator would show, it looks to me like the sum of the first 5 terms of the series gives a pretty accurate sum to the series, which is amazing. We just added up 5 terms and we have a decent sum to the series. Finally, number 5. This is setting up some stuff that you'll be seeing in Chapter 11. It's why we're doing all this. It's why I'm stressing you really have to know these tests, all of these tests, and what they look like and how to use them. Find all values of x for which the series 1 to infinity, x to the n over 2 to the n converges. And write your answer in interval notation. And I gave the hint that to me it kind of looks geometric. And that's because x to the n over 2 to the n can be rewritten as the fraction x over 2 to the n. Yes, that looks geometric. It looks geometric where r has the value of x over 2. We know a geometric series converges if absolute value of r is less than 1. Well, since r is x over 2, that means absolute value of x over 2 is less than 1. And then I can rewrite that absolute value inequality as -1 less than x over 2 less than 1. Multiply all 3 pieces of that compound inequality by 2. Gives me -2 less than x less than 2. So the given series will converge for any x you can think of in the interval -2 to 2. Pick any x in that interval. Put it into the original series, substitute it in for x, and you're going to get a series that converges. So, you know, again, when you watch the videos I put out there on a section-by-section basis, you should be taking notes on those videos as if, you know, you were in class, seeing how I'm doing the examples, everything I'm writing down. Practice the odd numbers when I ask you to practice them, and try to replicate, you know, what I'm really trying to get across in the videos. So keep working hard at it, folks. And that's it for going over this lab quiz. Thanks for watching.